Okay, so today is all about functions. Let's get started. Here's a brief recap from last time, examples of infinite loops. Let's just go through them really quickly. This one is an infinite loop because it starts out with y equal to 0, and it keeps on subtracting from y and testing that y is less than 10. It's always going to be less than 10 if you keep subtracting from 0. 0, -1, -2. It's always going to be less than 10, so that's an infinite loop. The next one, there is no test. So remember, the first thing is the initialization statement, then the test, and then the increment statement. There's no test, and so y, the body just keeps getting executed forever, and y keeps getting incremented forever. Here, it's a bit tricky in that this for loop has no body because of this semicolon. So it's always going to be testing this condition and then going right back and executing an empty body in this y++, even though it looks like it's the body of the for loop, it's really not. And here, there's nothing happening to y, it just starts out being 0, and it's always going to be less than 10 because we never touch y in the body of the while loop. Here, it's because of this assignment statement. We would expect it to work if there were one extra equals sign, but there isn't. So this assignment statement is going to return, in a sense, the number 2, which is a true value, and so this while statement is always going to be true. All right, so now let's take a look at loops. So take a second to think about which of these loops are different from the others, and if they're all the same, you can choose D. So assuming you've done that, let's think about all of these. If we just look at the initialization statement, the comparison, and the increment statement of this while loop, you can kind of turn it into a while loop, or of this for loop. You can turn it into the while loop by just taking the initialization statement, plopping it on the outside, putting the condition in the same spot, and then adding this increment statement after everything in the body is done. That's really what it takes to turn a for loop into a while loop, and vice versa. So these are exactly equivalent. So I guess the only question is, does this do while loop do the same thing? And the answer is no, because this will always execute. So this body of the do while loop will always execute once, and so if n were a certain value, like maybe 0 or -1, so x is not less than 0 strictly, or -1, that would be a false statement, and so neither of these two loops would execute at all, whereas this do while loop would totally execute once the body, because it doesn't check the condition until it's done the body at least once. So the answer would be C, it's not equivalent to the other two, to the first two. All right, now the big topic of today are functions. I assume you've seen functions before in like the Python sense, and they're very similar, if not exactly the same. The only difference is we care about the types now, because C++ is all about types. So there are 3 ways of using a function. There's, just like variables, you can declare a function, and what you've been doing with your main function, you've just been writing it and defining it immediately. So you know how to define a function, at least you've done the main function. And then to call a function is just to use that function with a certain arguments that will be substituted for the parameters of the function. All right, so let's look at the example from last time that I actually did for you, but let's go the other way. Let's start from the everything's in the main function and abstract that out to work with any n, and n would be the parameter of that function. So we're going to calculate the sum of this series using functions, and we're going to go a bit slower this time. All right, so let me copy the stuff from last time, sum series. It's this one. And I'll make a new folder for today. It'll be the 11th when you're watching this. So make dir 04-11, and I'll cd into that. And I will save this copy as sum series functions.cpp. So the name of the game this time is to do everything exactly the same, some series. We'll actually take command line arguments, and we already did that. Awesome. Oh no, we didn't. So let's take command line arguments. So that will involve using this argv. You don't need this const right now. So instead of getting n from cin, let's get it from argv. Yeah. So let's just assume the user did it correctly, or at least we can maybe make sure of it in a second. So yeah, let me do it this way. So let's just get it from argv like this. So we'll say n, we'll trust the user. N equals argv 1 and a to I that. And remember that I can use a to I because I've included this C standard lib library. I can use a to I because I included this. And I can also use stuff like cout and cin because I included iostream. And I promise I have a reason for writing these comments. We're going to get to making our own libraries in this lecture. So here we're taking n, and we've converted it from a string to an actual integer. These are a bunch of function calls, right? And assuming n is a nice value for us, we will perform this kind of this loop here, and this is what calculates the sum of that series. So what we want to do is make this into a function. So we'll bring it up here again, and let's work on this a bit slower than last time. So we have a function. We need to call it something. Like here's a to I. It's called a to I. Our exit is a function. Its name is exit. Ours can be, I guess, some series with an underscore maybe. Some series will be the name of our function, and it will take the n. That's what it needs to calculate the series, right? It needs to know about the n. So we have to provide that as a parameter to this function, int n. And notice that when I pass along this function, when I call this function, it's going to copy whatever I call it with, and it's going to call it n. So this n here, I'll get to this in just a second in more detail, this n here is completely different from this n here, all right? And this sum series function is going to do some stuff to actually calculate the sum of the series, and I'm just going to copy most of this. And the result, we need to declare a type, a return type, because this function is going to return the final answer. Return the final answer, and the final answer happens to be held in the res variable. So we can say return res, and this should be familiar to you, but the only change, the only thing that's really different from like Python is that we care about types. And so instead of putting nothing here, saying like def or something, we would say the type that this function returns. And so because res is a double, the type, the return type of this function is double. There are functions that don't actually return anything, that just do things, and we'll talk about those in a second. And some series takes one argument of one integer argument, which is how many terms to sum together. Okay, and I guess I've copied this twice, so I don't need this one. And now, instead of saying res down here, I can call the function. So a function call is when you say the name of the function and give it an argument. So n here in the definition of the function is called a parameter, but when we use it, this is called an argument, when we give it something concrete. So sum series with n, and these are two separate n's, remember that. I can maybe call this one m if I really wanted to, just to emphasize that m and n are completely different from each other. This n. I could have called it n down here. It would work just fine, but m works too. All right, so let's go and compile this and watch it run. All right. Oh, sorry, I saved this in the wrong folder. So let me move it from the 409 folder oh gosh, //409/sum series functions to here. Right, there it is. All right, G++ sum series functions.cpp. Oh, and we'll call it sum series functions. And I did something horribly wrong. Oh, and that horribly wrong thing was I wanted to trust my user and assume that they were going to give me an argument from the command line. And look what I forgot to do. I gave none. So I could say 5 like this and it would work. But we can also make sure that the user does this by using an assertion. Or we could just use an if statement. I think I want to introduce assertions a little bit later, so maybe I'll just use an if statement right now. So if argc is unequal to 2, say carr usage, you got to give the name of the thing, which is an argv0, and some n, and a new line. So now it'll work, and we should also exit if that was the case, because that was an improper use of this function. All right, so now that kind of error should never happen again. You know what's happening? It's saving this in 409 still. Oh gosh, this whole file is worried. Okay, that was the problem. I was working on the wrong file. Awesome. So you can disregard everything I've been trying to do for a couple minutes, and now it should work. There we go. Okay, so continuing, I'll have to remember to delete a lot of that. Okay, so now we have a working program, and we've made the sum series function. We've defined the function. This is called a function definition right here, because we're giving code, actual implementation, the actual code. All right. Now, we've also called this function, right? Down in main, we used the function. Function call is just a use of the function. We can also declare functions, just like we can declare variables. So this, right here, is called a function declaration, where you give the name of the function, give the name and the argument types, but not the actual implementation. And this lets the compiler know, oh, this is exactly how this function is going to be called and used, and it can wait a little while until it knows about the implementation. So if I didn't have this declaration, and I put some series below main, just the way that the compiler works, it's going to start looking for some series. It wants it to be defined before it gets called for the first time. So this is going to give me a compiler error. When I try to compile this, it's going to say use of undeclared identifier, because it doesn't know about some series, because some series is defined way down here. But I could declare the function. I could give its declaration and say, hey, this function exists, and I'll tell you about it later. And this cleans up your code quite a bit if you have a bunch of functions defined this way. This will also be helpful for when we start using libraries. So we can declare functions and wait to give their implementation. Okay? Now it'll work because the compiler knows that it exists, knows that this function exists, and it will eventually find it down there. And so it's still happy. It's going to be happy with this declaration before main, because now when it gets called in main, it knows about it, but it doesn't know where the actual code is just yet. So if I did this, it would also be a compiler error, because the compiler knows about the function, but when it goes to make the final machine code version of this program, it's going to be very confused because it can't find the actual implementation. So these things go together. And yeah, it's called a linker error. Can't find this thing called sum series. What are you talking about? I know it exists, but I don't know where is what it's saying. So function declaration, function definition, and function call. Okay. So now we've done this entire example. We've made the function. And now let's go back and make a function for drawing squares and triangles. So this should be very straightforward now. We can go and copy the stuff that we were doing last time. So like draw square, we'll take this, and I will be very, very careful to make this file inside of this folder. And we'll call this draw square with functions this time. Maybe I should say with functions. Yeah, there we go. And let's make our function called draw square now. I'll declare it and then define it below main again. So let's call this function draw square. And we're going to give it a parameter, right? The width and the height of the square. It's just one thing, right? We'll just call it size maybe. And it's an integer. But what should go here? What's the type? What does this draw square function return? So draw square is a special kind of function. A function that just does stuff, right? It outputs to the screen. It doesn't actually return anything because you're not asking for its value. It just does something. And the type of functions that do things but don't actually return things is called void. So this is called void, this function. You don't have to include a return statement. You don't need to return anything in a void type function, okay? And that's exactly what we want here, because draw square, it just is going to output at the screen and not actually return anything. There's no like return 0 in here. That's completely unnecessary. And actually, because of that, you can see why main is of type int, because it's going to return the exit type of the program, which is going to be integers, usually 0, sometimes 1, but usually 0. All right, so now, instead of drawing the square inside of main, excuse me, so we're going to call this function with size, I guess, instead of n. Whee! Oh gosh. Size times. And it's just going to do its thing and return on its own. You can optionally include something called this statement right here called return. That's how you can end a void type function early. There's like, you don't have to include anything else. You just say return by itself because there's no real value to return. But that's unnecessary here. So now we could just say draw square with n, and n will get passed along into size, and the function will go on its merry way and compute the thing that we wanted it to compute. So let's compile this, and it's in the right folder this time, which is good. Draw square functions, -o, draw square functions. All right. And yeah, we got to give it a parameter 5, and hey, it's working. 1, 2, 3. So this is pretty standard stuff. We made a function, we declared it, we defined it, and we called it. All right. So now let's go even faster. Again, remember that this is the statement that's, oh sorry, this is the statement that's going to change, because this inner for loop is what controls the width of the triangle. All right, and this will have to depend on the iteration variable from the outer for loop. So maybe I can just copy this one, draw triangle functions. Whee! There we go. And we'll go and just change this. So j is not size, it is I plus 1, right? That's how we had it. So now instead of draw square, it's called draw triangle. And yeah, everything should be pretty much exactly the same other than that. I plus 1 stars. I think, yeah, it should be fine. Let's just compile this and see if it's actually doing the right thing. Okay. Oops. There we go. Draw triangle functions like 5 again. Yeah, okay, so it's doing the same thing, and it's very similar to draw square. Okay. Now, let us talk about the stack. You might have seen this in a previous CS class, and I just want to really drive this home in this class because it's going to be very, very important, especially when we get to something called recursion. So the stack is the place where your local variables live. So local variables, let's go to our notes. Local variables are all your variables defined, or declared, sorry, inside functions, including the parameters. Now, you might not expect that. The parameters are also considered to be local variables. And every time you call a function, you make space in memory for all of its local variables. So when we call main, for example, when whoever calls main, maybe the terminal you say calls main, it's going to make space for a result variable, an x, and a y. And similarly, when we call sum inside of main, we're going to make space for the a and the b because they're parameters, which are also local variables. So let us just take this code and I guess we don't have to compile it. We know what's going to happen, right? We're going to make some variable called result, starts out being 0, and x is 10, y is 20. We call sum, that should return 30, or does it? And then we're going to output whatever result was. So I think, yeah, it would be best to just type all this out, and it's slightly difficult to copy for some reason. So let's take all this and make it pretty. And save this as, I don't know, should we call it stack.cpp? Sure. So here's this. Apparently main was not closed off. Sure. And let's make it nice. We can't forget to return 0, right? So there's a problem with the sum function. I hope you've seen it. I hope you can maybe see it. If not, I'm going to run this, and we're going to watch it fail. So g++ stack.cpp-o stack. And my compiler is actually being very nice to me, and it's telling me the problem. But let's run this program, stack. And oh gosh, result is 300? Or no, result was still 0, wasn't it? Let's make some endls here. So let's now recompile and rerun. Again, same error. So when we call sum, we go up here and it outputs 30. But it doesn't actually return anything now, does it? It's going to return result. I don't know if you can see my screen changing. I'll just do that just in case. It's not going to return 30 because this whole statement is really a void type. It does absolutely nothing. It just prints to the screen. It doesn't return the integer that it prints out. There's a difference between printing and returning things. So really, we're missing a return statement. And we are lucky enough for us to be returning 0, it looks like, which is quite nice. Maybe if we start result out at 42, we can see that sum is somehow implicitly returning 0 to us. Yeah, so the result would have been 42, but it's actually getting changed. So sum is somehow returning 0. But really, it could have returned anything. So on my machine, it's doing this. But this is something called undefined behavior. And I'm going to put it in all capitals just to scare you, because the compiler is allowed to do whatever it wants in this kind of situation. It could just like blow everything up. It's being nice to us and returning 0, but really it should be returning a plus b, right? That's what we want. So this is just printing. It's not giving the result back to whoever called the function. So now with all this, it's going to work, and let us draw the stack. So finally, all right, it outputs 30 up here, but then actually returns the 30. And so SumXY evaluates to 30 now, because that's what's getting returned. It's putting 30 in result and then printing out result. Okay, so let's draw this. Let's draw the stack diagram for this program. So here we go. Here is the stack. So it'll start like this, empty. We're going to call main. Somebody's going to call main. The terminal is going to call main. Your operating system is going to call main. Whatever you want to imagine happens, happens. And main has space inside of it for its local variables. Every time you call a function, space gets made for its local variables. Oops. Let me type that. Okay, which means for main we're going to make result, x, and y. Those are the 3 variables defined inside of main. I might have drawn this too small. Result, make a box for it, and then x, make a box for it, y, make a box for it. And now, result starts out being 42, x 10, and y 20. 10, 20. And then we go and we call the sum function. And whenever it returns, it's going to put its return value inside a result. So when we call a function, we make space for all its stuff, and we grow the stack. Stack grows every time a function is called. And we make space for its stuff. So this function is called sum, and it has local variables, a and b. We could also call them x and y, and they would be different from this x and y. But we're being nice and calling them a and b just to keep the names separate. And when we call the function, the values of its arguments are being placed into these parameter names. So we're calling sum with x and y, so 10 and 20, so that means a is 10 and b is 20. And then sum does some work. It's going to print out a plus b, so it'll do that thing like print 30, and then it's going to return a plus b. And so when a function returns, it gives back its result to whoever called it, so it's going to send 30 down to main, and then it's going to go away. Okay? We remove it off the stack when a function returns. The stack shrinks when a function returns. So really what I should be doing is like erasing this. But it's going to go away, and main is going to be the only thing left on the stack now. All right? But it got that 30 right before sum deleted all the rest of its information. Okay? So main got 30. And what did it do with that 30? Well, it was waiting to put it in the result variable. So it's going to update the result variable from 42 to be 30. And then it's going to go and it's going to print whatever's in result, which happens to be 30 now. 30, 30. And that's why the program does what it does. And then main itself is going to return to whoever called it, which is like your terminal, right? It's going to return 0. And then main itself, the program's over, main will go away, right? I'll just leave it here for posterity. But that's what the stack is doing. It's growing and shrinking whenever functions are being called. And it's this last in, first out principle that keeps track of which things go away. So the last thing that was on the stack is the first thing that goes away, it gets popped off. Just like when we called sum, it was up here, and it was the first thing to leave when it returned. Okay, And yes, all its local variables go away. And yeah, that was the stack in a nutshell. So now, here is the correct version of the function. We just went through this. And hopefully you can see the difference between printing and returning. So here, return gives back the result so that we can use it wherever it's called. We can assign it to stuff. Whereas printing doesn't actually, printing just outputs to the screen and gives nothing back to whoever called it. As we saw, it was returning 0 for me, just implicitly, this function. Well, what about this now? So here I have a sum function that we call sum. It doesn't actually return anything, and it calls exit 0. So what actually happens? Think about this for a second, and then now I'll go over it. So result starts out being 0. Let me just draw it actually. So again, we call main from like the terminal, or the operating system does it. Result starts out being 0, x is 10, y is 20. And then we call sum, and we wait for sum to finish because we'll put its return value into result. So we're going to call sum with a being 10 and b being 20. And then we immediately call exit. And exit just ends the program. So the entire stack goes away. And this function, or this entire program, it doesn't output anything. It never even gets to this line. I hope you see that. Right? And it was also incorrect for sum to not be actually returning anything of type int. That was an error. So that is all I have in the slides. I wanted to go through now just a couple things that are different. So here we have stuff that lives on the stack, right? Local variables and things. Local variables and parameters live on the stack. We also have global variables. So if I define a variable outside of any function, like int, I don't know, x, or no, we've already used x, int n equals 42. This is a global variable. Okay? And it lives outside of any function. I can talk about it inside a function. Let me actually make a new program to demonstrate this. So include iostream using namespace std, give me a main function. So I can cout n inside of main. Because it's a global variable, I can talk about it anywhere. I can use it inside of any function. And also, I can like add to it n++, cout n again. So this will print 42 and 43. Okay? But if we were to go and draw the stack for this now, we would call main. Yeah. Main actually has no local variables other than its parameters, argc and argv, which we didn't actually use in the previous examples. Main has argc and argv with some stuff in it. I don't want to draw it right now. But then also, just separately, in like its own little place in memory, the global variables live in a different place. And like n lives over here, it's 42. And we eventually set it to 43, right? So the stack, oops. and the place in memory where the global variables live are separate. They actually live for the entire life of the program. Live for the entire program. And any function can use them, right? Just as we showed here. You can use n down here as long as we have it like this. If I were to declare a variable here, also called n, this one would take precedence. Okay? And I would be updating this particular n and not this one. So it's important to not like override the global variables that you're using. So try to pick different names. But this is an example of global variables. And yeah, I think that was all I wanted to say about those. Another thing that I wanted to do was talk about separate compilation and making your own libraries. Okay? So what we can do is, I'll go into more detail with this later, but let's take our maybe draw square example, and let's split it up into, maybe I'll make a new folder even. Let's go down, we're here, spring, code from class, 411, draw square library example. So what I'm going to do is I'm going to put 3 files in here. I'm going to put a file that calls the draw square function, our code with the main function in it. I'll call it main.cpp maybe. And I'm going to add a few more things though. I'm going to separate all of this stuff. And this is going to be useful when you, in your labs and whenever you're writing code that has a lot of stuff going on, you want to separate all of those different concerns into different files. That's really a good thing to do and to get practice with. So I want to make something called a header file. So draw square.h. And inside of header files goes declarations, no implementation. And I'm also going to put draw square in its own little file called drawsquare.cpp. Usually when you have a .h file for header, CPP contains the implementation of all of those things declared there. So let's talk about this. Drawsquare.h is a header file. It contains the declarations of any functions that are in the current library you're defining. So we're making our own library. And drawsquare.cpp is the corresponding implementation file for drawsquare.h. So if you have any declarations in drawsquare.h, you should define them inside of drawsquare.cpp. And what we can do now is include our library. So include, just like IOStream, if I include that, I can get access to cout, and if I include cstandard library, now I can use exit and like A to I and stuff. And now if I include drawsquare.h, now the compiler knows about the drawSquare function. And what happens when you include something like this is that the compiler copies and pastes the file with that name inside of it. So you use those angle brackets for system libraries, so things that were included when you installed the compiler, and you use just quotes for your own libraries that exist in the same file or same folder. So somewhere inside the folder, you can give slashes and stuff. But drawSquare.h exists in the same folder as main.cpp, and so that's how it knows where to find it. And we know it's not a special system library because we're using double quotes. Okay? So this is how we define a 3-file example of using, this is called separate compilation. So we have 3 files. drawSquare.h contains the declarations of things. Main.cpp uses that declaration, and we include drawSquare.h, include the library. And drawSquare.cpp contains the implementation. And so now, to compile this whole thing, to compile this big program, we give all of the implementation files, g++, main.cpp, as well as drawSquare.cpp. Okay? So if we didn't give drawSquare.cpp, we're only copying and pasting drawSquare.h, and so we would get a linker error because we know the declarations of drawSquare, but we don't actually know the code inside, the actual implementation. We have to provide the compiler that implementation as a separate file. All right? And maybe we'll say -o drawSquare. That can be the name of our program. So this is how we compile it. Let me just put this like this or something. Okay. So this is inside of the, I didn't save it, inside of the drawSquare library example folder. So I have these 3 files, and I'll compile them this way. And guess what I forgot to do? Include, or use namespace std inside of the drawSquare.cpp file. It doesn't actually know about namespace std or cout. It's a separate file. And so you'd have to include it just like this, because it's being compiled separately. So there's that. Actually, a common thing to do is to never include anything inside of drawSquare.cpp except for the header. So you can add all these includes over here in drawSquare.h, and then just include drawSquare.h in drawSquare.cpp. And that will also solve that problem. It'll copy everything from here, including the declarations and the includes. So again, it'll work. And we can say drawSquare, and I guess we drawSquare 5. So this is a bit of a silly example because it's not a big program, but you can imagine that you have a lot of code and you want to split it up into these separate files. A header file that contains just declarations of things, the declarations of things in your library, a implementation file that defines, that gives actual code for all of those things that you declared, and then I guess a driver function or a driver file that just runs, that uses that library, that has a main function. Okay, so that's an example of that. And yeah, I think I want to give some examples of tests, but I'll do that in just a second. And I'll make a different video. All right, so now one last thing, I want to talk about what's called test-driven development. So it's called test-driven development, and this is really important for this class. And so the key thing is that programs are usually incorrect the first time you write them, right? Or they're untrustworthy. You don't trust your programs immediately after you write them, right? You don't usually trust them. Especially if you're given someone else's code, you shouldn't trust that either until you've looked at the code and actually walked through it, right? So you want some kind of confidence in your program, and tests are a good way to do that. To gain confidence, that your program is doing the right thing, you can write tests for that program. Yeah? So assuming you buy that, test-driven development is writing tests first. Write the tests before the code itself. Okay? And so you want to write all these tests and then write the code and then watch all of those tests pass or fail. If they pass, you know you can be pretty confident that you wrote the thing correctly, and if it fails, you know what to fix. So it really helps you understand what you're trying to write if you write tests before you write them. Before you write the code. So let's make a new file and just have a very simple program inside. So let's call it maybe I don't know, maybe just like some or TDD tests, test-driven development.cpp. So write tests first is the main thing that we're going to do here. I guess I need some kind of boilerplate here. Let me find something. This will work. So yeah, let's actually use this sum function. This would be perfect. So pretend for a second that we don't trust our sum function, which we really should, right? But pretend that we don't, and let's write some tests for the sum function that we're trying to define. Maybe I'll put sum down here and just declare it up here. So the function we're trying to test. So let's pretend that we want to test the sum function. And we're getting it from someone else. We don't trust that they implemented it right because maybe they like put a minus instead of a plus or something. So test-driven development, or TDD for short, write tests before code. So let's actually do this last. So let's make a function called sum tests, and we want to make sure test that, let's write a few tests just in comments. Test that 2 plus 2 is 4, right? That can be a test. Test that, I don't know, -1 plus 1 is 0. Test that 0 plus 5 is 5. Maybe that's enough to make sure that sum works correctly. You need to write as many tests as you think would convince you to make that it would work. So this function doesn't really have to return anything, it just has to keep checking things. So you can write a test like this. You can say if, and then we'll use the function. So sum to 2, we want that to be 4, right? That would be passing the test. So maybe if it's not, we'll say that the test fails. See error. Test failed. For 2 plus 2 equals 4, failed, exclamation point. End L. Something like that. And that's a completely valid way to write a test. There's also some built-in functions to C++, or even the C language. If I include another header, C assert, and let me just go to the implementation for this. There is a C assert library that contains really one function, just called assert, and instead of an int, we just assume that it takes a Boolean thing and it tests whether or not that thing is true, and if not, it'll tell you exactly what went wrong and where, which is sometimes really helpful. You'll be using these kinds of assert functions when you write your own tests in the labs. So another way to test this is assert and then give a Boolean valued expression inside of the assert function. So assert -1, or sum -1, 1 is equal to 0. So it's always assert and then Boolean expression. And this will stop the program if it goes wrong, actually. So it's a bit different from the first one. Then we can also use it down here. This is how we're writing tests. So this one line is a test that sum 0, 5 actually returns 0, or 5. See, that was an incorrect test before now. So this is what it means to write a test. There's a bunch of different ways you can, but this is one. And we can just run this function from main. And if we get no errors, sum worked. So let's write a function called sum using test-driven development. So maybe we can, actually just for the sake of example, let me put this other one first, -1, 1, 0, and then 2, 2, 4. Because now I can just say, oh, the sum of a and b, it's always 0. Yeah? So this is obviously incorrect. And the funny thing is it passes one of our tests. So it works sometimes, I mean, when those things sum to 0. So that's why it's important to have a bunch of tests, okay? So let me go back to this outer folder, g++ test-driven development.cpp. Gosh, that's a long thing to type. Let me just copy and paste it. And of course, it's not that easy. There we go, compiling, running. Oh man, see how it'll go in order, and see how it didn't say this first one failed? It says that the next one did though. Assert sum 2, 2 equals 4. All right, maybe the sum of everything is always 4. So it'll fail -1 plus 1 equals 0. It'll fail the first test and pass the second one and fail the third, and this assert statement stops the program on that particular line. It's really nice that it tells you the line too. It's like, oh, that one didn't work. So now if you give the actual real implementation, this should produce absolutely no output, which is the key. That's what we're trying to get at here. That's why tests are so nice. So now we run the program, it says absolutely nothing, and this is exactly what we want here, because it means all of our tests pass. And so this is your first taste of test-driven development, and hopefully you can see that it's going to be very useful when you're writing more complicated code later on in the class.